Okay, I think this sound should be working now. Okay, great, thanks. Sounds okay now? Yep, okay, I think the sound is okay. It might be a little bit worse, the sound, because I'm using a different microphone. It's not the high quality microphone. So I'm gonna try to figure that out by next week Monday. So I apologize in advance for any clicking you might hear, which is gonna be my my tablet. So this is gonna be the internal microphone on the tablet rather than the high quality external microphone. Okay, but it sounds like you can at least hear me, so we can get started. So we're going to talk today about gravitational potential energy. Just finishing that up in a few minutes, and then talk about satellite orbits, energy, and start with Keplers Law. I think now, because we lost another 5 minutes on this audio issue, that we might not get through all of that, but we'll try. Okay, so let's get started with gravitational potential energy. We introduced that last time, and we introduced gravitational potential energy at the end of Wednesday's class, and we derived gravitational potential energy, using our regular expression for potential energy. So the potential energy, or the change in potential energy, is minus the integral from some initial position to some final position of the force times dr. And in this case, we actually, if we just have a change in radius, if we only have a change in radius from r1 to r2, then that integral delta u becomes minus the integral from r1 to r2, or force is g times m over r squared dr. And there's actually a minus sign because the direction of the force is towards the lower radius, and so we're going to assume that r2 is greater than r1 in this case, for example. So if we plug in those numbers, we take the constants, put them out in front, we get g times big M little m, the integral from r1 to r2 of dr over r squared. So that's going to be, if we calculate that integral, minus g m times m, and then 1 over r evaluated between r1 and r2. So what that means is that we can use this expression, since this only depends on the difference between some value potential energy at the initial radius and at the final radius. We can actually introduce the expression for the potential energy as minus g m over m times m over r. And so that will be then u2 minus u1, the difference in the potential energy. Notice, by the way, that we could add a constant here, right? Again, this points out that potential energy doesn't have an absolute scale. There's the potential. We could shift that to higher or lower values, but we don't add any constant here, such that the reference point for potential energy will be such that at very large distances the potential energy goes to zero. So if we look at the potential energy as a function of the distance, if this is u as a function of r, it's actually going to look like this. And so at very large distances, if r goes to infinity, u goes to zero. Everywhere else, u is negative. And so the closer we get to the central mass, the lower the potential energy is. Of course, there's going to be at some point here a radius of the Earth, for example, and we're not going to be able to reach those parts of the potential energy space. But that's one of the areas where now we're going to be thinking of this potential energy as actually being negative. But there really is no difference. It's just a better way to describe this kind of force. So with this gravitational potential energy, we're of course going to have conservation of energy. So the total energy, which is the kinetic energy plus the potential energy, is conserved if there are no dissipative forces. So if there are no dissipative forces, then the sum of the kinetic and the potential energy will be constant. So one of the things we can do with that is actually determine the escape velocity. The escape velocity is the velocity v0 at the surface of the Earth, for example, or the surface of some star or so, or some other planet, such that we can reach the infinite distances, or in other words, escape the gravitational pull of this object. So we want to have this escape velocity such that we can reach large distances, even if at those large distances v will be equal to 0. So we asymptotically reach those large distances potentially at a very low velocity. So that means that initially, or E initial, will have to be E final, and E initial is going to be our kinetic energy, which will just be given by our potential, by our initial velocity, so 1/2 m v0 squared, plus our initial potential energy, which is at the surface of the Earth, so that's going to be minus g m times m over the radius of the Earth. And I'm not going to write the letter E here because that's going to be in general for any radius. So that's the initial total energy. The final total energy will be at R infinity, so the potential energy is going to be 0, and at a velocity that is equal to 0, so the kinetic energy will be 0. So the entire final total energy will be 0, and so we get as an equation that 1/2 m v0 squared minus g m times big M over r will have to be equal to 0. And of course we can solve that readily for this escape velocity v. One of the things you'll see is that the factors of little m drop out, so the escape velocity will be independent of the mass of the object that we're actually trying to shoot away or launch into space. We just have to make sure we get to that to that escape velocity, and the escape velocity will be 2 times g m over r with a square root. So what we're doing here, if we look back at the little graph I've drawn here, is we're giving an object at the surface of the Earth a kinetic energy such that we end up with a total energy. So now this is also a total energy axis, so that we end up with a total energy that's exactly equal to 0. So what will happen then is the object will go to a larger radius. It will remain at that same total energy. The kinetic energy contribution will decrease till it's 0, and the potential energy will increase. If we don't give that amount of kinetic energy, you can sort of imagine what will happen if we only give this amount of kinetic energy. Then the maximum radius will be the point where we don't have enough energy to go to a larger radius, and so we'll have a maximum radius for an orbit if we give an energy that is lower than the escape velocity that we would need at the surface. So that's the goal of this escape velocity. For Earth, by the way, if we plug in the mass of the Earth, which is 6 times 10 to the 24 kilograms, and then of course the radius of the Earth, which is 6,370 kilometers, and we plug in g, then we would find that this is about 11 kilometers per second. So if we want something to escape the gravitational pull of the Earth, we have to give it a velocity of 11 kilometers per second. And of course, the job of a rocket is to get to that 11 kilometers per second. And naturally, you need a bigger rocket to get to this velocity with a larger mass, because you'll need more force. So just as a reminder, the way we're doing this here is we start from the initial energy and the final energy that should be equal to each other. The initial total energy is kinetic energy plus potential energy, where the plus potential energy includes the minus sign in our potential energy expression. And then the final energy is 0, because the kinetic energy will be 0 at the final point, where we're infinitely far away, going infinitely slow. And if we're at an infinite distance, also the potential energy will be 0 because of the 1 over distance, 1 over r. So that's how we're deriving that. Notice, by the way, that this escape velocity, there's nothing in here that says this has to go in a radially outward direction. So if we have the Earth here and we're giving it an initial velocity that is outwards, then indeed we're going to go to infinity. But we could also have, we could launch here at an angle of 45 degrees, and we're still going to reach infinity just at a slightly curved trajectory. Obviously, we cannot shoot inside the planet because then we're just going to hit the ground. But the angle doesn't really matter here. It's just the magnitude, and the reason why it's just the magnitude is because we're talking about kinetic energies, and that turns the velocity into a scalar quantity. So the other curve, the curve that I've drawn here with the total energy E, it actually indicates a couple of things here, and I've sort of already indicated the different areas of this curve, right? If we give a kinetic energy that exactly at this point here, if the total energy is equal to 0, that's on that line, then we are just, that's the line that sort of separates two areas in this curve. It's the area where we have the green trajectories, where E is less than 0. Those are bound orbits, because there's a maximum radius we can reach. If we have E greater than 0, then we're above this curve. Now we actually, now we will have the ability to not just reach infinity, but actually we'll have some energy to spare. So we are able to escape the gravitational pull, not just with a 0 velocity, sort of an asymptotic situation, but we're able to escape the gravitational pull and have some kinetic energy to spare. So there's the difference here between bound orbits. That's really the concept that we're trying to introduce here. Bound orbits will have an energy that is less than the sum of kinetic and potential energy that you would need to escape the gravitational pull. And of course, the counterpoint to that is if the energy is positive, if the energy is greater than what we would need for simply escape velocity, then we can escape the gravitational pull. And of course, for those bound orbits, you can calculate this R max. You can calculate R max from the potential energy expression. So instead of solving for V0, you would be given, for example, the initial energy or the total energy, and you're trying to calculate R max, where the velocity will be 0 at that point. Okay. So let's see, so we've gone over this, the potential energy. So this is where we're going in our derivation. We take the integral from R1 to R2. The reason why we don't do this angular path, which is at a constant radius, is because for symmetry reasons we can actually ignore that in our integral. So let's look at circular orbits around Earth or around the Sun. So in a circular orbit, we're going to want to derive something. So in this case, this is a bound orbit. So the velocity with which we would have launched the satellite, or the rocket that the satellite was mounted on, would have been less than the escape velocity. But we want to calculate what the velocity is of that satellite in orbit. So let's take a look at that problem. So in particular for circular orbits. So for our circular orbits, we will have that the centripetal acceleration will be caused by the gravitational force, and so the centripetal acceleration I'm going to write it with a minus sign here because it's pointing towards the center, and that will be equal to the force, which also has a minus sign because it's also towards the center of rotation, towards the center of the Earth, and the force will be g times m, big M, over the r squared. Now we also know that the magnitude of the centripetal acceleration is v squared over r. So what we have is, if I drop the factors of m and I drop the minus signs, then we'll have that v squared over r will have to be equal to g times m over r squared. And this is the orbital velocity of the satellite. So you can see that, there's another factor of r that drops out. There's going to be a square root that gets introduced, and we get gm over r with a square root. Notice, by the way, that this is of course related to our escape velocity, or this looks similar to our escape velocity, which we had just derived here. Maybe I should have written escape here. So that's our escape velocity. This has a factor 2 here. In our case, we don't have a factor 2, so this is actually 1 over square root of 2 of the escape velocity. So it's always smaller than the escape velocity. If we're going in orbit, then we don't want to go at the escape velocity, but we will be going at a smaller velocity than the escape velocity we would have at the distance if we started off from that radius for that orbit. To some extent, that's a dimensional thing. The number of quantities that we have in our expression here are just the masses, the distance, and our factor g, and there's only so many ways you can put those together and get something that has the dimensions of velocity, and the way to put them together is multiply g by a mass and divide by a distance and take the square root. Then additionally, you can multiply a factor 2 in there. That wouldn't make a difference. But so it's somewhat unavoidable that the orbital velocity and the escape velocity are looking similar, because they're the only way in which you can get to a velocity from the given values and constants in our problem here. Notice that also this is independent of the little mass, the mass of the satellite. So regardless of what mass of satellite I put up here, whether it's the heavy International Space Station or it's a small CubeSat, it will have to go at that same orbital velocity. If I now plot the orbital velocity as a function of the distance or the radius of the orbit, it's going like 1 over square root of r, so it's going to look like something like this. And of course, again, there's the radius of the Earth here, so there's going to be a part of this curve that's not accessible. But above that, we're going to have the fact that at higher r, we're going to have smaller velocities, and we're going to have a lower speed, so lower orbital speed. From the orbital speed, from the orbital velocity for the circular orbit, we can calculate the period of revolution, the period of an orbit. So that's going to be 2 pi r over v orbit. And again, we can plug in the numbers here. We have order g m over r with the square root, and then we have another factor of r here, which is going to turn into an r squared when we put it under the square root. And ultimately we find 2 pi r cubed over gm with a square root. So the orbital period as a function of the radius over orbit, again with a region that's excluded because of the radius of the Earth. Now this is going to go like r to the power 3/2, so something like this, slightly higher than a straight line. So if I go to a higher radius, I'll have a higher period, or a longer orbit. So sort of, these things make sense if we go to a higher radius. The velocity gets smaller. At the same time, the distance for an orbit gets longer. So obviously the period will have to get longer as well then. Notice, by the way, that we could calculate what the orbital period at approximately the surface of the Earth would be. And if we did that, obviously there's nothing that is flying at the surface of the Earth, but if we pick it a little bit higher, at RE plus 300 kilometers, which is low Earth orbit, then we would find that the period is approximately 1.5 hours. So the orbital period of a satellite, most satellites that are in low Earth orbit, is about 1.5 hours. So that's how fast it goes around the Earth. So now that we have velocity, we have period. The one thing that we could still calculate is the energy in circular orbits. So if we have the energy, which is going to be kinetic energy plus potential energy, so 1/2 mv orbit squared minus g times m little m over r. We can plug in the expression for v orbit, which, as a reminder, was square root of gm over r. If we plug in the square root of gm over r, and we take the square again, so we get gm over r, what we find is this is 1/2 gm m over r minus g m over r. So again, these two expressions start to look very similar, and they end up being minus 1/2 gm m over r. So the total energy in orbit is, as a function of r, it's going to look like this. That's our minus 1/2 gm m over r. Notice that this is always negative, so it's a bound orbit. And this is the total energy. The total energy is half the total potential energy, so there's going to be a potential energy that is here. And the difference is, of course, the kinetic energy in v orbit. So that's the kinetic energy that shifts that curve upwards. So the difference between just having potential energy and being in a circular orbit is that it shifts the energy curve upwards. Okay. And we could draw the energy curve here, of course, as well. So if we just write the kinetic energy, that's going to be our always positive component here. That's 1/2 times v squared of v orbit squared, and so this curve is actually the square of this curve, right? Or it goes like the square of this curve. That's why it looks sort of similar. Okay. So that's all we wanted to talk about in terms of circular orbits. We could there's this derivation that Newton came up first in terms of circular orbits, and of course there the idea was that if you have a little cannon here and you can shoot a little further and a little further and a little further, and at some point you shoot just as fast with your cannon, so that the cannonball goes into orbit and hits you back on the head. Sort of a Looney Tunes situation where something goes in orbit and goes around the entire planet. So these are all circular orbits, and that's a little bit of a simplification. In fact, it's a large simplification. Really, we have to go to Keplers laws. Let's see, I'm back in the wrong color here. We have to go to Keplers laws to describe the proper orbits around planets. And the first of Kepler's laws is that, and this requires a little bit more math to derive this. We're not going to go through the math to derive this, but you can prove that Kepler's laws are satisfied for any inverse square force law, and so it is true for gravitational force. In this case, we're going to use it for gravitational law, but this would be true for any force law, that is 1 over square root of the distance. So the first of Kepler's laws, here we go. So the first of Kepler's laws says that all orbits in a inverse square law, force law, are ellipses. And I'm going to put here all bound orbits are ellipses with the Earth, Sun, or whatever object you're spinning around, with the central mass at one of the foci. If we have an ellipse here where this little mass is going around the larger mass, then that larger mass has to be at the focus, at one of the two focus points in the ellipse. And so here the planet is going around the sun is at the focus. Now, since this is an ellipse, there's two mathematical parameters we're going to introduce. E is the eccentricity. In other words, how much like an ellipse is this orbit? And we're going to introduce a distance parameter A, which is we're just going to call it the size of the ellipse. And with those two parameters, we can write the equation for the ellipse, just the shape of the ellipse, no time evolution. And that's going to be alpha over r is 1 plus e times the cosine theta. That's the fundamental equation for the mathematical equation for an ellipse. And we can look at a couple of specific examples. So for e equal to 0, what we find is alpha over r is 1. So r is alpha, and that's constant. So this is what we call a circle. That's what we call a circular orbit. That's just a special case of the ellipse when we don't have eccentricity, when the eccentricity is equal to 0. When the eccentricity is between 0 and 1, we get an ellipse. So now in this case, alpha over r is 1 plus e cosine theta. So that will be between 1 minus e and 1 plus e. So in the case of 1 minus e, that's when the radius is largest. In the case of 1 plus e, the radius is smallest. But the radius is always a finite number related to this parameter alpha. And then we can have e equal to 1. At that point, there's going to be a possibility that alpha over r becomes 0. When 1 minus 1, when we have theta equal to 180 degrees, then we find 1 plus e times cosine theta is going to be equal to 0. And that means that r goes to infinity for theta equal 180 degrees. So this is going to give us a parabola shape. And then finally, we can have e greater than 1, which is when we get a hyperbola. So those are the different kinds of trajectories that Kepler's law predicts, Kepler's first law predicts. So for bound orbits, we get ellipses. For any orbit, we get other shapes. So this is the ellipse. So for any orbit, we get what are called conic sections. So sections that you would get if you take a plane and you cut a cone along that plane. If your plane is perpendicular to the axis of the cone, you get a circle. If it's at an angle, you get an ellipse. If it's parallel to one of the sides, you get a parabola. And if it's more than, if the angle is even larger, then you're going to get then you can get hyperbolas. So those are the conic sections that are described that any inverse square law force will cause masses to describe, or the orbits that are described in any inverse square law equation. Now we can use this for a number of things, and one of the examples that's treated in the book is this Homan transfer. What we can actually do is we can relate the total energy which we've derived in the case of our circular orbit. We can also write something very similar for elliptical orbits. In fact, if we look back at our total energy expression here, minus 1/2 gm m over r, the total energy in the case of a bound orbit, an elliptical orbit, will be, for an elliptical orbit, will be minus 1/2 gm m. Now not over r, but over a. And a is the semi-major axis, which really is just a way of saying it's, let's see if we have it here. We don't have it on any of these drawings, but it's half of the distance, half of the longest distance in the ellipse. So it's half of the distance on the line along the focus points. So half the distance from here to here. And you can see that in the case of a circular orbit, that reverts to r. So if E is equal to 0, if the eccentricity is equal to 0, we find that the semi-major axis is equal to the radius. So we recover our original energy expression. So we can use this energy expression to calculate what energy I would need to have, what total energy I need to have at my launch here to get into this elliptical orbit and to be able to arrive at Mars in this case. And then at this point here, I have to increase my my energy again to be able to get into this orbit, which has an even larger semi-major axis, right? And so these are called Homan transfers. It's a common orbital transfer, even around Earth for satellites. If you want to go from one orbit to another, you are in a almost circular orbit at first. You go into an elliptical orbit, and then you go back into a circular orbit there. And the transitions to go into these different orbits, they correspond to delta v, or changes in velocity, and those changes in velocity increase the energy, in particular the kinetic energy at this point, and that change in delta v is usually what then in science fiction shows looks like a burn, or there's an impulse that is given to the object to increase the energy. So that's all Kepler's first law. There's two other laws, and I'm not going to go into them in detail because they require a little bit more derivation. Kepler's second law says that if a planet is going into an orbit, the surfaces it describes in different parts of the orbit, it sweeps out equal surfaces A1, A2, and A3 in equal times. And this is really coming from conservation of angular momentum. If we're at a larger distance here, we're going to have a lower velocity, and the angular momentum is actually related to the surface area that we're describing here, because that's the product of kind of distance and velocity. So conservation of angular momentum leads to the surfaces described by the planet or swept out by the planet to be equal in equal time. So going from A to B takes the same time as going from C to D, takes the same time as going from E to F. That also relates to the fact that the velocity is slower at larger distances than it is at closer distances. And then finally, Kepler's third law, and I think I have the wrong, this is actually still a second law. There's no drawing for Kepler's third law, but Kepler's third law relates then the total orbital period to the size of the orbit. And it actually relates the total orbital period to the surface area of the entire ellipse. So if you think about it, second law is looking at the different surface areas along the ellipse. If we look at the entire orbit, what Kepler's third law says is that, okay, I don't have time to write it down, is that the square of the orbital period is proportional to the third power of the semi-major axis. So again, half the distance along the longest line in the ellipse. So those are the three laws. And of course, Kepler's third law we can also use to derive, for example, what an orbit would be if we are at a different size, at a different semi-major axis for the orbit. It is one of the things that we can use to derive, based on observations of the solar system, what the mass of the sun has to be, because the proportionality constant between orbit and semi-major axis is actually dependent on the mass of the sun. So sorry I had to go a little bit quicker through these last, through the Kepler's third law and second law, but I hope that that there will be it will be clear in the textbook after reading over it again. On Monday we're going to then start to look at the special relativity. And so that will just be the last two lectures looking at time and length dilation. Time dilation and length contraction. Okay, that's it for today. So talk to you all on Monday.